All right, hello. All right, here it is. You've had me in class long enough now to know that one of my deisms is, let's see the big picture. Because sometimes you just need to back up and you need to look at the big picture and kind of understand where you're going for everything to make sense. You are now entering into a discussion on what we're going to call what is called stoichiometry, okay? Which is the calculation of quantities in chemical reactions. You know that we've been talking about chemical reactions. You know that we've been talking about balanced chemical equations. So now we're entering into a topic of study called stoichiometry. But here's the deal. In stoichiometry, we are going to continue our use and discussion of balanced chemical equations. Now, what does a balanced chemical equation represent? It represents some type of chemical reaction. And we understand that a chemical reaction is different than a chemical change is different than a physical change, because at the end you're going to have something different. So you have reactants and you have products. So here goes. We are really going to look at the arithmetic of equations. The equations that we look at will be balanced chemical equations. Now, as we look at those balanced chemical equations, there are going to be certain relationships, okay, that we can use to our advantage. We're still going to be using some of what we call the line method or some of what we call the fractional method. We'll still be using and almost, doing some conversion work and things of that nature. So we are going to look at balanced chemical equations, okay? We're going to look at quantities or pieces of information that we can get from those equations. And we're wrapping it under the title of stoichiometry, okay? So, in one of the textbooks that I use, they gave an example, and the example was of a tricycle. So the tricycle represents the product, all right? Well, obviously the parts that would go together to make the tricycle would represent the reactants, okay? But here we have one product. So understanding this little analogy that I'm going to give you will kind of help you understand, what a balanced chemical equation is, but even more so, it will help you understand how we can get certain ratios or certain relationships, okay, within this product. Let me show you what I mean. So according to them, which makes sense, you have F plus S plus 3W plus H plus 2P equals FSW3HP2, and you know that these are subscripts, so that means you have 3 of these and 2 of those. Now before you get too confused or whatever the case may be, it's pretty simple. You have one frame, you have one seat, you have 3 wheels, you have 1 handlebar and 2 pedals. Okay, well that's not very difficult to ascertain. Well, what does that give you? It gives you FSW3HP2. So what is this? That is the formula, the chemical formula for one tricycle. Okay, well, so here it is. If it's going to be balanced, then what you have in your reactants, must also be what you have in your products. Okay, and we've already harped on the law of conservation of mass. You know that we don't just create matter, and you know that we don't just lose it. It can't just go poofy. You might produce a gas that escapes into the atmosphere, but it still has to be accounted for. So this would represent our idea or our notion of a balanced chemical equation, so to speak. What you have versus what you have. All right, so understanding that, then here's a question which you're going to say, Mr. Day, I don't need to do this to get the answer. And I understand, you just need to see the main point. So if they say, we want you to make 640 tricycles, that's what we want you to make. How many wheels would that take? Well, you guys are smart kids. You're automatically just going to multiply 640 times 3. I know that and you know that. That's not what I'm after right now. What I'm after is there's a relationship here that you can use to your advantage, okay? And the relationship comes from this chemical equation. So make no mistake, big picture, we're going to use chemical equations to look at quantities. So the information is coming from the equation. Well, we already know that for every tricycle, it takes 3 wheels. So you say, oh, well, that's a relationship between reactants and products. Yes. It takes 3 wheels to make 1 tricycle. Well, the other beautiful thing about this, which I know you already understand, is that you know that this and this is going to cancel out, because by this point in time, you're becoming experts with the fractional method or the line method of conversion. So you say, all right, well, that cancels out and that cancels out, and this is the only unit that I'm going to be left with. So when I do my math, I get 1,920 wheels. Okay, well, at this point, I don't really care about the number. I don't really care about the example. What I care about is the notion that you're seeing the big picture, which is, okay, I can use chemical equations to find certain quantities, and there are going to be relationships within the equation that will help me figure these things out. Yes, okay, that's the main point. So, a balanced chemical equation can be interpreted in terms of different quantities, including, number 1, the number of atoms. Number 2, molecules. So what am I really saying? How many do you have? Number 3, moles. Well, what am I really saying? How many do you have? Number 4, mass. And number 5, volume. Now, these are the items or the quantities that we are going to examine in this lecture at the very beginning of this unit on stoichiometry, which is the arithmetic, in this case, of equations. So, one more time, what were the 5 quantities again? Well, how about if I want to know the number of atoms? How about if I want to know the number of molecules in a balanced chemical equation? Number of moles, mass, and volume. So, being the intelligent people that you are, you know what I'm going to do now. I'm going to start relating these 5 items to a chemical equation, all right? So here we go. So number 1, let's consider the number of atoms. Now, this is also going to be fairly easy to you, big picture-wise, because you already know how much we've harped on balanced. You know how much we've harped on the law of conservation of matter. So here we have a diatomic nitrogen, we have 3 diatomic hydrogens, and we have the creation of NH3. Well, the beautiful thing about this is you've already covered enough information in my classroom that you also know that this is a synthesis or a combination reaction. So we have 2 items coming together to make this item. Now, it turns out that the state of matter are gases, but I don't know that that's real relevant right now. What is relevant right now? Okay, well, let's look. How many nitrogens do we have? We have 2. How many hydrogens do we have? We have 6. So, is this balanced? Well, here I have 2 nitrogens, and here I have 6 hydrogens. Remember, I multiply that through. So, yes, Mr. Day, it is balanced. Okay, but that's not really the question per se. The question is, what is the relationship between the reactants and the products in terms of the number of atoms? And I'm thinking you're already a step ahead of me and you're going to say they better be the same. Yes, they better be the same. So I have 2, I have 2, I have 6, and I have 6. So when I look at the arithmetic of a balanced equation in terms of the number of atoms between the reactants and the products, they better be the same. Okay? All right. Number 2 and 3. Now you might be like, well, how come you're gonna put moles and molecules together on this slide? Because don't we want to know about how many moles we have or how many molecules we have? Why are we putting them on the same slide? Because if you know how to do one, you know how to do the other. So it's like killing 2 birds with 1 stone, as the old saying goes. So here we go. You have your N2, your 3H2, and your 2NH3. We already know that equation is balanced because we've already used it. So we look at it and we say, okay, how many molecules? Let's start with molecules. How many molecules of each do I have? And remember, we're comparing the reactants to the products in a balanced chemical equation. So what do? We look right here and what do we say? We say 1. Now, there's not a 1 there, but the absence of a number is not the absence of a number. It's understood to be 1. So I have 1 molecule of diatomic nitrogen, 1 molecule. Well, what about right here? Well, I look at the coefficient. This coefficient is guiding me. And I say, okay, I have 3 molecules of diatomic hydrogen. Very good. Now, how many molecules of NH3 do I have? Well, I have 2. Now, before you allow this to confuse you, don't. Remember, this is a chemical reaction. In this case, it is a synthesis or a combination. I'm putting 2 things together to make 1. Okay? So, let's talk totals versus, reactants versus products. Well, 1 and 3 are 4. I have 4 molecules on this side, but I only have 2 molecules on this side. Okay? Now, what about moles? And you're like, well, Mr. Day, I'm not really sure how to find it. Once again, yes, you are. Look at your coefficients. Okay? You mean it's that easy? Yes, it's that easy. Look at your coefficients. So my coefficient of 1 tells me that I have 1 mole of N2. My coefficient of 3 tells me that I have 3 moles of this. Okay, but how many moles of product do I have? I have 2. Okay? I have 2 moles. So I think we need to consider this very quickly one last time. How many molecules? 1. How many molecules? 3. How many molecules? 2. 1 plus 3 is 4, and where I come from and where you come from, 4 does not equal 2. So what does that tell me about molecules in a balanced chemical equation? It tells me that they don't have to be the same. I don't have to have the same number in the reactants and the products in terms of the number of molecules. But what else does this information give me? And there's the beautiful thing. It gives you a relationship. You can think about this if you wanted to make a fraction. In other words, how many N2s does it take to make this? It takes 1, but how many do you get? You get 2. Ooh, so that would be a fraction, or could be a fraction. Well, how many of these does it take? It takes 3, but how many do you get? You get 2. So there is a possible ratio or a possible fraction that we could create, okay? All right, now what about moles? Well, you say, Mr. Day, you already told us a while ago. Look at the coefficients. Yes, so 1 and 3 is 4. That number is 2. So what does that tell us about the number of moles in reactants versus products? It tells us that the number doesn't have to be the same. So far, let's think about this. That number was the same. This number doesn't have to be the same. And this number does not have to be the same. Okay? All right, well, let's go to the next one. What if I wanted to examine mass? What if I wanted to examine mass in a balanced chemical equation? Well, I hope you're 2 steps ahead of me now. Okay? I mean, I do hope that when you watch these things, you do what you need to do to be successful. Maybe you rewind them, maybe you look at it again. I don't know, but I do hope you're not just listening. I hope you're thinking. We have pounded so much on this idea of the conservation of matter, you should already be 2 steps ahead of me on mass, right? And you should already intuitively know we don't create mass and matter, right? I mean, we don't create matter, which has mass. We can't destroy it, so it better be accounted for. So you already know the answer to this one. You know that number darn well better be the same. All right, but you can do this and calculate it mathematically by doing what? By using molar mass. And you know how to go to the periodic table and do that. You know to go to the mass. We go to the 10th place and round and knock off the AMU and add a G. I mean, it's pretty simple, right? But we also have to consider how many we have. We need to consider, our numbers. So we look right here and we say, okay, that's easy, Mr. Day. I can calculate the mass of this, all right? So I have 2 of them at 14.0, so the overall mass of this is 28.0 grams. I know here that I actually have 6, okay? So I'm going to multiply 6 times 1.0, and I'm going to get 6 grams of H2. Well, if you add those 2 numbers together, you know they're going to be equal to 34. But when you look at your product, you're just simply going to take the molar mass of 2 of these, and when you do, you're going to find out that you're just simply multiplying 2 times 17, and you're going to get 34. But this is not a surprise to you because you expected to get 34. Why? Because you had 34 here. So you fully expected to get 34 here in order to meet the law of conservation of matter. So continuing to think, big picture, thinking about what we're doing here. We're looking at balanced chemical equations, and we're examining what quantities we can get from those, right? So we pretty well know that the number of atoms better be the same on both sides. We know the number of molecules and the number of moles doesn't have to be the same. But what have we just discovered? Well, we discovered that number 4 goes hand in hand with number 1, right? And we know that number 4, you better have the same mass on both sides, okay? Now, let's finish with volume, okay? And we know that volume, by definition, is the amount of space something takes up, right? We know that volume, by definition, is the amount of space something takes up. We're also very familiar already with Avogadro's hypotheses, which states that at STP, and you know that that means standard temperature and pressure, okay? We want to have an apples-to-apples comparison, all right? But at STP, a volume of gas, 1 mole, that volume will occupy a space of 22.4 liters. You already know that. You know that. So if you know the number of moles, right? Okay, so let's think about this. All right, so here we go. So we're going to look right here, and here's what we're going to say. We're going to say, all right, that's understood to be a 1. We just have 1 mole of N2, right? I mean, we're continuing to use the same equation. We know how to find the number of molecules and the number of moles. We covered that together at the same time. So I have 1 mole here, I have 3 moles here, and I have 2 moles here. Well, I would anticipate that 1 mole would occupy a space of 22.4 liters. I would anticipate that 3 moles would occupy 3 times that amount, right? Okay, well, here it is. 2 moles would be 2 times that amount, right? Well, you know what? I didn't even finish the math right here. If I did finish the math, I think you would be able to see that it would be 89.4 liters, right? Well, that doesn't equal 44.8. Okay. Now, let that sink in for a minute. Because what do you have going on? You have a chemical reaction. You have a synthesis or a reaction where we are joining items together, a combination reaction. You know, what is the idea behind a chemical change, behind a chemical reaction? Well, our products and our reactants aren't going to be the same. They're going to be different by definition. If they weren't, then it wouldn't be a chemical change. So what are we learning? What is the overall item that we are learning here? We just discovered that the volume is not the same on both sides. Now, you recall that what are we discussing in this lecture? We're beginning to discuss stoichiometry. We're beginning to discuss the arithmetic of balanced chemical equations. We're beginning to understand quantities that can be derived from a chemical equation. But at the end of the day, we're going to learn about these 5 quantities, but we're going to learn something very interesting. We're going to learn that only 2 of them had to have the same equivalent values on both sides. And that was what? It was the number of atoms and the number of mass. Oh, well, that makes sense. They're very much tied together. But the number of molecules and the number of moles and the volume does not have to be the same on the reactants versus the products. All right, and so this information is important for us to know. It's important for us to realize. But what's really important is that we also now understand that we can look at that equation and we can look at the information that it contains, but we can also take information from it. We can take values from, that's what we've been doing this whole time, is getting different values and talking about different values or different quantities. And we can create, different fractions from that. We can look at different relationships and we can use that information to our advantage, okay, by doing simple math, by using the fractional method or the line method, okay? So this is the purpose of this first lecture, to make sure we understand kind of the relationship that exists with these 5 quantities to a balanced chemical equation.